Geometric unified field theories excel at explaining the physical universe from higher dimensions. By extending spacetime into a fifth dimension, these frameworks successfully derived the mechanics of both gravity and electromagnetism from pure continuous geometry. From this deterministic foundation, they also extrapolate advanced wave structures. They can successfully derive the behavior of the Dirac equation without introducing external forces. Yet every one of these frameworks hits a mathematical wall when attempting to explain quantum measurement and the Born rule. The math stalls here because continuous geometry does not natively yield non-uniform probabilistic weights. Deterministic systems output deterministic results. They do not naturally produce the localized probabilities required by quantum mechanics. To locate the mechanical point where this mathematical failure occurs, we will conduct a reverse foundational decomposition of two massive theoretical corpuses, charting exactly where their geometric logic breaks down. This decomposition suggests that the inability to derive probability is not a derivation failure, but a result of an architecture where geometry and probability exist in separate layers. This comparative matrix pits two distinct geometric frameworks against each other. On the left is the 1980 Williams text on five-dimensional thermodynamics. On the right is the modern oscillatory dynamics transductive bridging theorem, or ODTBT. We grade both using an epistemic stratification standard that separates every equation into one of three layers. Red is L1, the foundational axioms. Blue is L2, the mathematics derived directly from those axioms. And yellow is L3, the parameters that are empirically fitted or imported from outside the system. Both frameworks possess high density in the derived L2 layer. They are mathematically rigorous when calculating purely structural mechanics. Look at the Williams corpus. He successfully applies Weyl gauge principle to deterministically derive discrete wave modes entirely within that L2 derived layer. But while those discrete wave structures form as intended, there is no mathematical trace of a probability distribution within the derivation. Both models easily derive wave geometry, yet neither generates probability weights. This isolates the exact location of the structure probability gap. To see how physicists attempt to bridge this probability gap, we look at the modern ODTBT side of the matrix. ODTBT constructs an outcome scaffold defined by 12 symmetrical Voronoi basins, knopped across a four-dimensional manifold. The native mathematics of these symmetrical basins produces a uniform distribution. Geometrically, the chance of every outcome is exactly 1/12. But physical reality is not uniform. To match observed quantum behavior, the model relies on blocking assumption A1.4. This assumption forces a non-uniform distribution over the geometry. It achieves this using a cosine² function, which is strictly an L3 imported parameter. It is fitted to match observations rather than derived from the underlying geometry. This use of a blocking assumption illustrates that purely deterministic phase space geometry does not inherently generate the Born rule. We now pivot to the 1980 Williams text to examine how his five-dimensional thermodynamics handles that same mathematical boundary. Williams takes a different approach. He refuses to import L3 probabilistic weights, preserving the purity of his L2 derivations. In Chapter 13, Williams draws a line. He rejects quantum probability as a foundational reality. As this diagram shows, Williams constructs mechanical entropy deterministically. He treats statistical mechanics, and by extension, quantum probability, as a derivative approximation. While this preserves mathematical purity in the L2 layer, it does not explain the empirical probability distributions observed in experiments. Williams and ODTBT arrived at the same mathematical border. One preserves structural purity by excluding probability, the other preserves empirical accuracy by importing it. This divergence highlights a structural impasse that geometry alone has not resolved. This three-tier diagram represents a unified architectural model that explains the paradox. The structural successes of both models, geometrification, mass, wave mechanics, and 5D viscosity, belong exclusively in the bottom tier, layer 0, the deterministic substrate. The Born rule and probability weights belong in the top tier, layer 2, the phenomenological level. They are physically isolated from the foundational geometry at the bottom. Between them is layer 1. This is a transductive interface where structured deterministic data flows upward and scatters into statistical distributions. This is the state-bearing substrate hypothesis. It suggests that probability is a phenomenological emergent property, not a foundational geometric primitive. This model removes the requirement to force the Born rule down into the continuous geometry of layer 0, treating the probability gap as an expected level boundary. This shift in focus suggests that rather than forcing probability into geometric equations, the research becomes a study of the interface, a transductive mapping of how deterministic geometry results in the statistics we observe.